So now we're going to start to look at classification, but to bridge this part of regression and classification, and also to help understand the differences between regression and classification, we will start with this logistic regression that is actually a classifier. We're going to use it as a classifier, but which deep down is computing a regression. So I'm going to give a brief introduction to classification, this idea of linear separability, and we're going to use linear models here. Logistic regression is a linear model, but then we're also going to apply this idea of how to, by projecting in higher dimensions our data, we can go beyond the limitations of a linear model. So first, this idea of separability. Let's suppose we have this data set. So in this case, the blue dots represent normal cells and the red dots represent tumor cells, and the features here, so the two axes are two feature values, two things that we measure in order to make the prediction about the class, are the activities of two different genes. So depending on the combination of activities of these genes, it's more likely that the cell is normal or a tumor cell. We say that these classes, in this case the normal and tumor cells, are linearly separable if we can separate the data set that we have in these two classes using a linear combination of the features. In this case we have two features, so we have our data in two dimensions, and this linear combination of these two features will result in a straight line here separating the two classes. But in general, you can imagine that you could use the activities of 20 genes, for example, and in that case you will have these data in 20 dimensions. And in that case, it would be linearly separable if you could find a hyperplane in these 20 dimensions that would cut the two classes without errors. And the frontier that we have here, separating the two classes, is a linear discriminant. So one thing that we can see that is different between classification and regression is that in classification we are not trying to approximate some line to our data, rather we are splitting our data by cutting according to some discriminant, to some separation. And since we are using a linear model, this is a linear discriminant. In two dimensions, it's a straight line. If we were working in three dimensions, it would be a plane, but in more dimensions, in general, it would be a hyperplane. It may happen that the classes in the data set are not linearly separable. So this is the same example, but using two other gene activities. And in this case, you still see that there is a difference between normal cells and tumor cells, but the frontier between the two is curved here. We cannot separate these with a straight line without making mistakes, because the blue one is down here and then there are red ones a bit higher up. So these are not linearly separable in this case. Okay, so let's approach classification again with as a linear problem, with a linear model. And in regression, when we were doing that regression with a straight line, with this linear regression with this formula, we had these two parameters. So we had this θ1 and θ2 that defined the line that we were going to use to predict y, to predict the continuous value based on x. In classification, we don't need just the line, we also need to know which side of the line corresponds to which class. So more generally, if we have a hyperplane in n dimensions, we need to know which side of the hyperplane corresponds to each class. So it's not enough to just draw this line here. We need to know that normal cells are on this side and tumor cells are on that side. So in this case, what we can do is we define this general hyperplane, or this line in two dimensions, by using a perpendicular vector that indicates the positive class. So we can specify the linear discriminant in this way. This would be the vector of features. You can have, in this case, for example, we have two features. This W here would be a vector of parameters that we use to multiply by the features, and this is an extra parameter that will set our plane or our line higher or lower in the coordinates. And the division between the two classes occurs when this expression is exactly 0. On one side, this expression will be negative because this product will be, this part here will be smaller than 0, and on the other side, it will be larger than 0. And basically, if the feature vector is more in the same direction as the parameters vector, this inner product here will be negative. If they tend to oppose each other, if they are in the same direction, the inner product will be positive. If they tend to oppose each other, the inner product will be negative. So this gives us the definition of a separation between the two classes that is positive on one side and negative on the other. So, for example, if we had in 3 dimensions, in this case we have 3 features. If we have in 2 dimensions, this expression is this line but with a perpendicular vector pointing to the positive side. If we have 3 dimensions, then it's a plane with a perpendicular vector, this vector W here, pointing to the positive side. But we can generalize this for n dimensions. We cannot visualize it, but this applies to any size of these vectors. And it's always a straight discriminant. So it's a linear discriminant because it's always a linear combination of the features. So this is the frontier function. The y of x is given by this expression. We do the inner product of this perpendicular vector that we compute by optimizing the parameters and each data point, and we also add this W0. So it's positive on one side, negative on the other, and we can separate the two classes in this way. So now, how can we find the best way to put the discriminant? In order to help understand this problem, I'm going to start doing it the wrong way. So this will give us the wrong result, but it will help us understand what's different between what we've been doing with regression and what we have now in classification. So let's think that we want to find the best values here for W and W0, so that it's negative on one side, corresponding to class -1, and positive on the other side, corresponding to class 1. So we could imitate what we've been doing with linear regression and try to adjust these parameters in order that they give us as close as possible to -1 when we have things in class -1 and 1 when we have examples in class 1. So we could minimize the quadratic error. In this case, the target value would be 1 or -1, it's the class, and the function would be this function that we have here, that we are going to adjust these parameters W in order to minimize this error. So this is actually easy to implement. Let's load the data on this gene expression. We have these carbonic anhydrase and this guanylate cyclase activator, and these two give us this plot here. Sorry, I'm going to show this one. So they give us this plot that is linearly separable if we combine these two features. So we have the data here. This 1 or 0 indicates the class, tumor or normal, and we have the values for the features. Okay, so one complicating factor here is that we are choosing our classes to be 1 and -1 because it's positive on one side of the discriminant, negative on the other, but actually the classes that we are reading from the file are 0 and 1. In some cases, you can, in general, when you're using libraries with these machine learning algorithms, you may not need to pay too much attention to this because they generally can incorporate different labels, but it's a good idea to pay attention to these details because they may lead to some mistakes when you're actually using the class values. So in this case, we need to remember that we have to convert this into 1 or -1. But it's actually easy. All you need to do is multiply by 2 and subtract 1. So if it's 1 multiplied by 2 is 2, you subtract 1 and it's 1 again. But if it's 0, you multiply by 2, it's 0. And when you subtract 1, it's minus 1. So that way you can convert the 1, 0 into 1, minus 1. So let's rescale our values again. What we saw in the previous lecture was just a very simple way of doing rescaling, which was dividing by the maximum because we only had positive values. Here it's a bit more complicated because we have negative values and positive values, and so and we can do something a bit more sophisticated, which is basically we're going to do a standardization. A standardization is a form of rescaling our data so that the new values will be distributed with a normal distribution. So have a mean of 0 and a standard deviation of 1. So approximately normal depending on how they're distributed, but the mean and the standard deviation will be 0 and 1 respectively. So how we can do this is to subtract from each of the original values the mean of all the values that we have in our data, and then divide by the standard deviation. So if we subtract the mean of the resulting set of values will be 0, and if we divide by the standard deviation of the resulting set will be 1. So this is standardization. We rescale everything so that the average is 0 and the standard deviation is 1. Another way of doing rescaling is normalization, where we subtract the minimum value and then we divide by the difference between the maximum and the minimum. So this rescales everything into being between 0 and 1. It's a more sophisticated approach than what we saw in last lecture. Basically, if we have the general intuition or the assumption that our data is approximately Gaussian distributed, then it's best to use standardization because you get that bell shape neatly around the 0 mean here. If we have something that has a fixed range, for example, if you are dealing with color values in images or things like that, then normalization may be a good idea because you just rescale the range to 0 and 1 and you keep the same general distribution in that fixed range. In any case, it's important to store these parameters because these are rescaling values. It's like changing the units that you're using. And so when you're going to apply your hypothesis to new points, you need to do the same rescaling again. So we can do this here. We're going to load our data. We're going to separate the class labels, which is the last column of our data, into these Y's matrix. This is a matrix with a single column. That's why I used these square brackets here. So I retain the same shape of the column. And this is a matrix with all the previous columns. So the two features here. In this case, note that the x is not a single value, but for each point we have two x values. We have the activity of one gene and the activity of the other, and this tells the position of the point. The y value, the one we're trying to predict, is the class label. Ones are tumored, the others are normal. Okay, so we have the data here. We're going to rescale. We're going to compute the mean and the standard deviation and rescale the feature values. Note that it makes no sense rescaling the class labels because the class labels are simply 0 or 1 in this case in the file that we read, and they just indicate which class the example belongs to. In the regression example, we also rescaled the target values so to keep everything within more reasonable ranges and avoid problems with numerical errors and so on. But in this case, the class labels, it makes no sense to rescale them. Okay, one thing that you're going to see sometimes in the literature is a simplification of this expression. Instead of having the coefficients that multiply the features in this inner product separated from this constant that determines if the plane is higher or lower, we can rewrite this expression by adding a 1 to the features. So we have all the same features plus a 1 at the end for all the points, and including this constant in that vector there. Because when we do this inner product, we are doing the multiplications and adding all the multiplications here, all the products here. So if we have a 1 at the end of the vector x, and if we put this w0 inside this vector 2, then we have at the end we are adding w0 multiplied by 1, which is the same as adding w0. So what this does basically is, by adding this 1 at the end of x, we can simplify the expression to just use a dot product. I'm going to do that here. This requires a bit more code, but the reason for this is so that when you see this in the literature, for example in Bishop's book, you don't get stuck there not understanding what this is. So this is basically just doing this simplification, and this is how it could be done with code. So you create a new matrix that has the same rows as the original one, but one more column than the original one, and it's all filled with the value 1. So it's basically this shape with an extra column, all filled with 1s. And then you copy the original data to the first columns, so all except the last one, and the last one will retain that one here. So now all we need to do is to compute this prediction is just to do the inner product of the coefficients of the parameters and these expanded features. Okay, so now let's fit this with minimizing the quadratic error so that we can see what goes wrong in this case. This is the incorrect approach, but we need to see why it's incorrect. So we're going to create this cost function that we're going to minimize. We have the set of parameters that we are trying to adjust. So these, I called it theta here, but these are all the w's that we have, all these w's plus the w0. And we have the matrix of our expanded values, so the original features plus this one at the end, so we can do just the dot product there. And we have the target classes. Just remember that the target classes in our data set are 1s and 0s, and we want to convert these to -1 and 1, but we can do it like this, it's easy. So basically what we do is we create a vector of coefficients that is the same length as this vector here, but in a column, so that we can do the dot product between the matrix and the coefficients. So basically what we're going to do here is this inner product that we have here between two vectors, the vector of features for one point and the vector of parameters in our model. We are going to do this using NumPy over all the data at the same time. So this X matrix has all our data points in rows, and we're going to multiply each of them using the dot product by the vector of coefficients. So in order for this operation to work with the rules of algebra, we need for this to be a matrix with a single column. It cannot be just an array, it has to have a column. So this is one way of doing it. You create a matrix that has one column, and then you copy the values into that column. Another way of doing this would be to use reshape, which is a method that you have in NumPy arrays. Later on I will show some examples in other lectures. Okay, so now we have the coefficients. We compute the inner products. Sorry. We compute the inner products for all our data set here, and this will now give us all the predictions, all these y values for all our data. And now we can compare all these predictions with the class labels. So we have all the predictions here. The class labels, we convert them into -1 and 1, and we compute the quadratic error. So this is basically our approach. We compute all the predictions, we compare the predictions to -1 and 1, which are the class labels, and now we minimize this. If you want to minimize a function with Python, it's easy using this optimize optimized model in SciPy. So you have this minimize function, and you just give an initial guess here. So in this case, I'm going to start with a guess just having all parameters starting at 1. But then the minimize function will go down the loss function, this shape of the loss function to find the minimum. And the function that we want to minimize, we give it as the first argument. So this quadratic cost will be the one that we created here, which measures the mean quadratic error between the predictions and the target classes. And now we have this result of the optimization. In the x field of this result, we have the final coefficient values. So this way we can minimize and look at the result. We have the coefficients, we can compute the line that divides the two classes, and we get this result. So basically what happened here, this is not a good result because we did not manage to separate the two classes. We are trying to make it so that those on the positive side, so in this case the positive side will be this one because tumor is class 1, so those on the positive side will be as close as possible to 1, and those on the negative side as close as possible to -1. But the thing is that as we go further and further from the discriminant here, the value of y will change. So as we go further from the discriminant, this y will increase. And since we want all the points on this side to be close to -1 and on this side to be close to 1, these points that are further from the frontier will pull the discriminant to this side. So this is something that is good when we're doing a regression, because we want the points to pull the line to be as close as possible to the data. But it's not something that we want when we are doing classification, because in classification what really matters is to split the two classes in the right place, and we don't particularly care if we have some points that are very far away from the discriminant, as long as they are on the correct side of the discriminant. So if they are on the right part of the division, then they're okay, and it doesn't matter if they are far away. So this is an example of an important difference between regression and classification. So fitting with least mean squares does not give us a good result, because it makes the points that are far away from the discriminant start weighing more on the position of the frontier and pulling the frontier to the wrong place. We want to penalize something that is away from the line in regression, but not in classification. And this gives us a more intuitive notion of the difference between regression and classification. In regression, we want to approach the data as closely as possible. In classification, we want to separate the two sets, and we don't particularly care if we are close to the data or not. In fact, it's even better if we manage to separate the classes with a discriminant that is far away from all the points. Okay, so now let's look at logistic regression as a way of solving this and building a classifier. Instead of trying to approximate the data itself, suppose something analogous to what we did with regression, where we assumed there was some function that related the x, the features, to the y, the value that we're trying to predict. In this case, let's assume that there is a function that gives us the probability of a point with some features x belonging to class 1. So this is the conditional probability of being in class 1 if it has these features x. Now let's assume we don't know what this function is, but somewhere in the abstract space there is this function for our particular data. And so if we have this function, if we can measure the conditional probability of belonging to class 1 given for each point, we can consider the separation between the two classes to be that hyperplane where the conditional probability is the same for each of the classes. So the conditional probability of belonging to class 1 is the same as the conditional probability of belonging to class 0. So where the probability is the same is where we're going to split the two classes here. And since these are probabilities, the probabilities are the same of these two events, which are mutually exclusive, when the probability of belonging to class 1 is the same as 1 minus the probability of belonging to class 1, because this is 50% on either side. So in this case, logistic regression is doing a regression, but for this probabilities function. We're going to try to approximate this continuous estimate of the probabilities. So deep down, it's a regression. But since we are going to use this cutoff at 50% probability to separate the two classes, we will be using logistic regression as a classifier. The trick here is that to find an adequate function that gives us the correct placement of the discriminant. So this, in general, this will be we'll have arbitrary number of features. So in our examples, we can consider 2 features, but we could have different data sets with more features. And based on these features, then for each point that we want to classify, we're going to predict the class for which the conditional probability is higher. So basically, if the conditional probability of belonging to class 1 is over 50%, we predict it's class 1. If it's below 50%, we predict it's class 0. Okay, so we assume this function that gives us the probabilities. We have the plane here. And since these are probabilities, we can also rearrange this in this way, that the place where the plane will cross, so where the probabilities are equal, the probability of belonging to class 1 divided by the probability of by 1 minus the probability of belonging to class 1, this will be 1, so the logarithm of this will be 0. By rewriting this expression using the g there and assuming that we are trying to find the hyperplane, so we have a linear classifier, we can rewrite this in this way. The plane that where this is at 0, the logarithm of our function divided by 1 minus the result of our function, will be defined by these parameters. So these are the parameters of the discriminant we're trying to find. And rearranging this equation, we will reach the shape, well, what the function g must look like. So this is what function g must look like in order to get this result. And this 1 divided by 1 plus e raised to minus the inner product plus that w0, this function here is basically the logistic function. So has this shape like an S. This is a good function for approximating probability estimates because it ranges from 0 to 1, so it works well for probabilities. And it has this property that it levels off at very low and very high values. So this is very different from what you have in the quadratic function when you're trying to minimize the quadratic error, in that as you go away from the frontier, the value rises very faster and increasingly faster, and so points that are away from the frontier start pulling harder than those that are close to the line. In this case, points that are far away, as long as they are on the right side, they will just be okay, because you'll just have a high probability of belonging to that class or low, and so it will not have that effect of pulling the line away from where it should remain. Okay, so let's now try to find this set of parameters, again by maximum likelihood. This is the same thing we did in linear regression, but in linear regression we assumed that we had a function that predicted y and had some normally distributed error. In this case, we don't have a function that predicts a continuous value. We have a function, or this continuous value in our data, we have a function that predicts as the continuous value the probability of belonging to some class. So the likelihood of the parameters is the probabilities that we estimate of all those points belonging to their respective classes. And this we can compute directly from what the function is giving to us. So points that belong to class 1, we just use the value that the function g is giving. This is the probability of belonging to class 1. Points that belong to class 0, we use 1 minus the probability of belonging to class 1. So one neat trick of doing this in just one product with all the data is to raise each of these values here, g and 1 minus g, raise them to the class or 1 minus the class. So when point n belongs to class 1, this value here, t of n, is 1 because that's the class, and so we take this value here in the product. This one will be raised to 0 because if the class is 1, 1 minus 1 is 0, and so this part will be raised to 0. But anything raised to 0 is 1, so this is simply ignored. Basically, if the point belongs to class 1, we use the value g in this product. If the point belongs to class 0, then we use the value 1 minus g, because now this one is 0 and this one here is 1. So what we are doing here is we are computing the product of the probability of point 1 belonging to class 1, point 2 belonging to class 1, and so on and so on. And or if they belong, or the product of the probability of point 1 belonging to its class, whether it's 1 or 2, point 2 belonging to its class, whether it's 1 or 0, and so forth. So we are multiplying all these probabilities, and this will give us the likelihood of the W vector that we have. We can do the same thing as we did with regression. We take the logarithm of the likelihood, and now this product becomes a sum. All these powers here will come down here. We get the logarithms of the functions, and this will be the expression that we have here for the likelihood. So the difference here is that in linear regression, we were assuming we had a function that approximated the target values with some error. With logistic regression, we assume that we have a function that approximates the probabilities. And now for the maximum likelihood, it will give us different results, but the idea is the same. We are computing the probability of our data given the parameters of the function, so multiplying the probability of each point belonging to each class over all the data set. And then we take the logarithm to get the logarithm of this likelihood, because maximizing the likelihood will give us the same set of parameters as maximizing the logarithm, and the logarithm becomes much easier to compute because now it's only a sum and not the product, so we don't have those the same risk of going into overflow or underflow and things like that. And actually maximizing the likelihood is the same as minimizing the logistic loss or the cross entropy. So basically the error in predicting the probabilities. We can change the sign here and if we divide by the number of points, instead of getting a sum, we get an average, but the expression is the same. And so this is the logistic loss, and it will be the function that we're going to minimize. So once again, maximum likelihood the same as we did with regression, with linear regression, but the final expression is different because now we are assuming different things about what we're trying to do. And this is the function of our parameters. So this g here is 1 divided by 1 plus the result there of the inner products and adding that constant. So the expression that we had for the plane, the linear plane that separates the classes. Okay, so let's start with an example where we have linearly separable data, and we're going to classify in this way. You are not going to be doing this in detail, writing the code, because we can use logistic regression from the library, but I'm just going to step through the code so that you have a better idea of how this is working. So first we're going to implement this function here, the logistic function of some argument that we receive there. So this is just 1 over e raised to minus this x that we receive, and this x value will be this computation for all our data. So note that since NumPy allows us to do these operations with broadcasting, this can be an array of values, and we can do this computation for all the array in one go and return an array with all the computed values. Now we need the function to the cost function to minimize, which is this one here, the logistic loss. So what we can do is we receive a set of coefficients here in this theta. We just change this to a column like we did before, so that we can compute this dot product here. So we can compute these values here by just doing the dot product. This is exactly the same that we did here in this other example, okay? Using the dot product here. And now we need to feed this into the logistic function. So when we do this dot product, we send the result to the logistic function. We get all these g values. So this now we are computing these values here based on the data and these coefficients that we have, the w's there. So once we have all these values, we can now add these two parts. So each one, the logarithm of each one multiplied by its class, and the logarithm of 1 minus each of the value multiplied by 1 minus its class. So this means that those that belong to class 1 will use only this part, because this part will be 0, and those that belong to class 0 will use only this part, because this part will be 0. So this is what we're going to add here. We take the logarithm for those that belong for class 1 and for class 0, and then we add the two, and we take minus the average of this. So remember that we are minimizing, so we need to minimize the symmetric of the function. The logistic, the likelihood function would be something that we were trying to maximize. But this is easy. You can always do maximization by changing the sign on something and then minimizing. Okay, so now we do again the same thing that we saw here, use SciPy, minimize and so on. I'm going to skip this part because it's the same. It's just that we are using a different cost function, but now the result looks better. So this way, when we are doing the regression, not for the actual values of the class, but for the probability of belonging to the class, and we use this logistic function that has this property of flattening out away from the frontier, now we can put the frontier in a more reasonable position, because these points that are away from the frontier, it doesn't matter, they are all class 0 and they all count as 0, and then the logistic function rises here, and all these that are class 1 will count as 1, and so the discriminant gets placed between the two classes. Okay, so what if we don't have linearly separable classes? If we try to do this with this data set, we don't get a good result, because it's not possible to draw a straight line dividing the two classes here without errors. The frontier is curved, so with a straight line we cannot do this. And logistic regression is a linear model, because we have here in our function g, we simply have a linear combination of parameters and the features we receive. So this will always give us a straight plane, a linear discriminant in whatever space we are working in. But we saw this trick that we did with linear regression, in that we can expand the features with some nonlinear transformation and then do a linear classification in this expanded set. So to do that, we are going to, by the way, we're not going to use this implementation now. So we are not going to implement logistic regression by hand, because this is very inefficient and then has numerical problems and so on. So in practice, we are going to use the logistic regression class from scikit-learn. This is another linear model, one for classification, and we do it the same way. We create the object, and then we fit with the data. Now here this C is a regularization factor, which for classifiers in scikit-learn is a number that the actual weight of the regularization in this case is 1 divided by C. So if we use a very large number for C, this means that it's a very low regularization. When we reach support vector machines, we'll see why they use it in this way and not some alpha or lambda or something like that, like we do in regression. But for now, we'll just leave it like this, use very low regularization, and this is the tolerance for when the computation finishes, when optimizing the parameters. So what we can do to use logistic regression for sets that are not linearly separable is to expand the dimensions of our data using a nonlinear transformation. For example, we can add a term that is the product of the two features. We have these two features here, the two gene activities, and we are dealing with data in 2 dimensions. And so we can add a third dimension that is simply the product of these two. We can create a new matrix that has 1 more column than the original data that we had, and we copy the original matrix for everything except the last column, and in the last column we put the product of the two features that we have. So this expands our data to 3 dimensions, and now we fit the logistic regression to that expanded data. So we use the expanded data to fit here, and we get the values from our matrix with the class labels. So this is what happens when we go from 2 dimensions to 3 dimensions using this product of the two features. You see that now the data is spread out in 3 dimensions, but with a curved surface, because this transformation by adding a third coordinate with the product of the first two is not a linear transformation, so the data got bent. But now the discriminant is still linear, only it's linear in 3 dimensions, not in 2. And we are cutting this bent surface using a straight plane. So when we project this back to our original space, the intersection of the two is actually a curve, because we bent our data in this 3-dimensional space. And we can do this with more features. So just changing the code here, adding more, expanding with more features, we can add, for example, not only the product of the two x1 and x2, but also the square of each of them. And now we get 5 features, and we are doing logistic regression in a 5-dimensional space. It's still a linear classifier, but now it's classifying linearly in 5 dimensions using the twisted set of data that we create here. And now when we project it back to our original space of 2 dimensions, the frontier has this form here, and now we can approximately classify all of this correctly, but we can keep increasing. For example, 7 features, 9 features, and so on. We just add new features computed using nonlinear transformations of the originals. Of course, now we meet the same problem we saw with regression. As we start increasing the power of our model, we start overfitting the training data, and we get hypotheses that become less plausible. For example, this one tells us that any point falling there will belong to the red class again. Because now in this 9-dimensional space, the data is so bent and twisted that we get these strange separations of the classes. And this is probably overfitting. We would not expect a point falling there to belong to the red class instead of the blue class. So we're going to see this in next week, how to deal with overfitting in classification, but basically the idea will be similar to what we saw in regression. We have model selection and we have regularization. So now we saw this idea of separating classes linearly, linear separability if they can be separated linearly, and using a linear discriminant. In arbitrary dimensions, this would be a hyperplane. If you use 2 dimensions, it's just a straight line. In 3 dimensions, it's just a plane. But we can use any number of dimensions just by adding more features. We saw logistic regression as a way of finding the discriminant to separate the two classes. We saw that using minimizing the quadratic error would not be a good idea, because separating the two classes is not the same as trying to fit a line as close as possible to the points. So using least mean squares does not work in this case, but logistic regression is a regression to some hypothetical function of the probabilities of belonging to each class. And if we try to approximate that function, we can then use a cutoff point of 50% to separate the two classes. So next lecture, we're going to see this how to handle overfitting in classification. We're also going to see cross-validation, which is a better method of using validations. But we met again this idea of we cannot separate things linearly in the original space that we have, but we can create other features with nonlinear transformations and go to a higher dimensional space where a linear separation will allow us to solve the problem. In practice, we will not do this in manually, but we will use, when we see more sophisticated algorithms that do this implicitly and without having to do expensive computations. Okay, next lecture we're going to see then how to solve overfitting here in classification. I'll just turn off this microphone and change things, and I'll meet you in the Zoom meeting.